Hello everyone, good evening to all of you. Welcome to ACE Preparation League 2. So as part of this, today we are going to have a discussion on important concepts of operating system. So if you look into our previous session which is being conducted on yesterday, in that session I have pointed out the important concepts with respect to main topics, right? So among them, I'm going to discuss the important concepts in this particular session. So as part of this, first if we verify introduction and background of operating system, as part of this we have listed around 5 subtopics. Among them, the first subtopic, which is the most important one, is location. So as I clearly mentioned in our previous session that in this particular subtopic, we will be discussing, we can discuss about a concept called dual mode of operation. Dual mode of operation, which is the most important concept which is dual mode of operation. So what is this dual mode of operation? So this we want to know. So for that, let's consider a simple program. So here, dual mode, what is the meaning of dual mode? So we are having two modes here. So a system can have two modes here. One is user mode, and another one is kernel mode. There are two modes we are having. So here, if you verify, your operating system can allow the CPU to execute user instructions as well as kernel instructions. User instructions you can call as non-privileged instructions. Kernel instructions you can call them as privileged instructions. So I can say the instructions which are executing in the user mode, those instructions are non-privileged instructions, and the instructions which are being executing in the kernel mode, those instructions are said to be privileged instructions. So means CPU operating system is allowing the CPU to execute both non-privileged instructions as well as privileged instructions. So while it is allowing the CPU to execute privileged instructions and non-privileged instructions, the execution order should keep on change from user mode to kernel mode and kernel mode to user mode. So you know that. So in order to distinguish at particular time, in which mode of instruction is being currently in execution, in order to know that, we use a bit called mode bit. So this mode bit is distinguishing which in which mode currently we are. In which mode of instruction is being currently in execution by the CPU. So this mode bit is sometimes it can be 0, sometimes it can be 1. So when the mode bit is being set to 0, then you are saying that it is part of kernel mode. If the mode bit is set to 1, then you are saying that this is user mode. So like this we are saying, right? So it means that while you are moving from kernel mode to user mode and user mode to kernel mode, you are doing some shifting paradigm. That shifting paradigm is said to be mode shifting. So how this exactly the mode shifting is happening? So this we are going to see in this session first. After that we can solve some questions based on this dual mode of operation, and then we can see the rest of questions, the rest of concepts also, right? So how the mode shifting is happening, like from kernel mode to user mode and user mode to kernel mode, how it is happening, that we are going to see by considering one example. So let's look into one example here. So for example, I have a program like this. So a simple program I am writing, like this is a main function. So I'm having some instructions here, and now there is one privileged instruction, or else a system call is being invoked here. A system call is being part of my program. That system call name is fork. So what is the meaning of system call? So system call means, you know that the system call means, so the definition for the system call if you want, so you can write like this. So system call means, right? So in order to get any kind of service. So system call, it is a call, right? It is a call. So it is used to get any kind of service. It is used to get any kind of service, any kind of service from operating system. Any kind of service from operating system. So this is what your system call main function, right? So system call is used to get any kind of service from operating system. It is used by the user program in order to get any kind of service from operating system. So this one of the system call is fork system call. So this fork system call is part of your user program. So when this particular fork system call is invoked, then what will happen during the kernel during the compile time, this particular fork instruction is being converted to during the compile time, this is being converted to SVC. So what is this SVC? SVC, which stands for supervisory call. SVC, which stands for supervisory call. So during the compile time, when we start execution of this system call instruction, which is privileged instruction, then this during the compile time of this particular fork instruction, it is being converted to SVC. And this SVC during the runtime, this SVC generates a software interrupt. It generates a software interrupt. So this software interrupt, you know that interrupt means obviously every interrupt can have an interrupt service routine, an ISR is there. So this software interrupt is associated with a component called ISR, which stands for interrupt service routine. So this interrupt service routine does two things. It is having two functions. What are the two functions it can do? The first function is it can do mode shifting. One is it can do mode shifting. So this is what earlier we have discussed, like shifting from user mode to kernel mode. So changing the mode bit from 1 to 0 or else 0 to 1, that is called your mode shifting. That can be done by this ISR. And this ISR, in parallel to this, it also maintains a table called dispatch table. It also maintains a table called dispatch table. So this dispatch table, as it is a table, it can have entries, right? It can have entries. So these entries are for every system call. For every system call, we can have an entry in this dispatch table. So if you consider one system call is fork, then fork along with this, its starting address, its base address, you can say, its starting address, base address can be part of this particular dispatch table. So when this fork system call's base address is being loaded into, so it means that this particular fork is part of the main memory somewhere with the starting address. This is, let's say, x is the starting address and it is going on till some x plus n. So this is the code of, this entire memory is the code of your fork instruction, right? So this fork instruction is having this much code as part of your memory. This is when this base address is being loaded into the program counter, then the execution will start from here. So this is the way exactly happening. So here, when this fork system call is being invoked, then this fork system call is being, during the compile time, it is converted to SVC, which is supervisory call. And this supervisory call during the runtime, it is being converted to software interrupt. It means that you have entered into kernel mode here. So far you are in user mode. When you start executing this fork system call, then you have entered into kernel mode. So it means that you have changed your mode bit from user mode to kernel mode. So this is a privileged instruction which can be executed in the kernel mode only. So means once you have encountered this fork system call, then your execution is in kernel mode. So when you can come back from kernel mode to user mode, that can be done by, see, look at in this fork body, this is the body of the fork, whatever the last instruction of this fork we are having, whatever the body we are having for the fork, the last instruction of this particular fork body can enable you to move from kernel mode to user mode. user mode. So this is the way how you are moving from user mode to kernel mode and kernel mode to user mode. So this operation is said to be dual mode of operation, right? So where this generally where this mode bit is being located, this mode bit is being located as part of the CPU only, central processing unit, our processor. This processor is having a register called PSW, program status word. So this program status word is a register in which the MSB bit, if you consider this bit, you can say that it is the mode bit. So your mode bit is part of the CPU, and specifically your mode bit is part of program status word register, PSW register. So this is what the location of your mode bit, and who is this mode bit from 1 to 0 and 0 to 1 in the sense your interrupt service routine, that's what we have mentioned, which is this is responsible for mode shifting, right? So until you are in execution of these instructions, you are in user mode. Once you have started execution of this fork, then you are entering into kernel mode. Then once you execute this last instruction of the fork, then again you are moving from kernel mode to user mode. So here kernel mode you can call it as privileged mode, and user mode you can call it as non-privileged mode. So this is what exactly what this dual mode of operation. So I hope you are clear with how when we are moving to kernel mode from user mode, and when we are moving from kernel mode to user mode with this particular diagram, right? Or else you can say that with this explanation you can understand that how this mode shifting is happening. Yes or no? So then if you have understood this concept, then we are moving into some questions based on this particular mode shifting. Look at, this is one question we have, like a processor needs software interrupt to, option A, test the interrupt system of the processor, option B, implement coroutines, option C, to obtain the system services which need execution of the privileged instructions, and option D, return from subroutine. So a processor needs software interrupt. See, look at if you correlate this question with our explanation of this diagram. So where you can see software interrupt here. So what this software interrupt is doing? This software interrupt is allowing you to get some system services. I mean, in order to get some system services, or else in order to get some services from operating system, you required a privileged instruction called fork, and this fork is indirectly generating this software interrupt here, because this fork instruction during the compile time, while you are executing this fork instruction during the compile time, it is been converting to supervisory call, and this supervisory call during the runtime, it is being converted to, it is generating the software interrupt. So when you are generating this software interrupt, the main intention, or else whenever you start execution of some system call, what is the main intention? The main intention is in order to get any kind of service from operating system. So based on this explanation, you can easily able to answer that this particular question answer is what? Option C. In order to obtain the system services which need the execution of privileged instructions, we require this software interrupt. So when the software interrupt is being generated, it means that the privileged instruction execution can be happened. This is what your explanation for this question. So this is enough. So this particular concept is enough to answer this particular question. Look at, there is one more question based on this dual mode of operation. This is the question we have. A CPU has two modes. One is privileged and non-privileged. In order to change the mode from privileged to non-privileged, from privileged to non-privileged. What is the meaning of privileged here? As I clearly mentioned that privileged mode in the sense kernel mode. And what is a non-privileged mode? User mode. Kernel mode to user mode you are changing. Means you are already part of the privileged mode. Okay, you are already part of the privileged mode. So a CPU has two modes. One is privileged mode and non-privileged mode. In order to change the mode from privileged mode to non-privileged mode, option A, a hardware interrupt is required. Option B, a software interrupt is required. Option C, a privileged instruction is needed. Or else option D, a non-privileged instruction is needed. So which one is the answer here? So if you verify this particular concept, whatever the diagram we have mentioned here, this diagram. So first, in order to enter into privileged mode, you required a privileged instruction. In order to enter into privileged mode, you required a privileged instruction, means via software interrupt it is. And then look at this particular concept. So while you are executing this fork system call, this is the body of your fork system call in the memory. As I clearly mentioned that the last instruction of this fork, can allow you to move from kernel mode to user mode. So this last instruction of the fork itself, it is a privileged instruction. So the body of fork contains some instructions, those instructions are all privileged instructions only. So the last instruction of the fork is allowing you to move from privileged mode to non-privileged mode. So it means that a privileged instruction is needed to move from privileged mode to non-privileged mode. So hence, what is the answer for this question? From this explanation, what you can answer to this question? The answer for this question is option C. A privileged instruction is needed in order to move from privileged mode to non-privileged mode. The last instruction of the fork system call is allowing you to move from privileged mode to non-privileged mode. Hence, you can say that option C is the answer for this. So if you want to answer these type of questions, compulsory you must be aware of this particular topic, which is the most important topic. This is dual mode of operation topic is very, very important here. So I hope you are clear with this topic, where the mode bit is being located, who is responsible for doing this mode shifting, what exactly the mode shifting is, and when you are moving into the kernel mode, when you are coming out of the kernel mode, all these things we have discussed with respect to this dual mode of operation. So I hope you are clear with this concept, and the questions which we have, these questions are also, explanation of these questions are also clear to you, right? Right. So now we are moving to the next important concept as part of this introduction and the background of operating system, which is types of operating systems. As part of types of these operating systems, you have 5 types of operating systems. Yesterday we have clearly mentioned in our session, like 5 types of operating systems we are having, like batch operating systems. If you recall, batch operating system is there, and then multi-programmed operating system is there, multi-programmed operating system is there, multi-programmed operating system is there, and then multitasking operating system is there, multitasking operating system is there. After that we have multiprocessor system is there. So we have listed some operating systems, right? Multiprocessor system, and we have also mentioned real-time systems, real-time systems. So these are the important types of operating systems we have. Along with this, we have distributed systems also, right? But these are the main contents. Among them, if you verify the previous year gate questions we have from these batch systems, multi-programmed systems. These are the which are very important. So now we are going to have some idea on these batch systems and multi-programmed systems, and then we can see the questions based on these batch systems and multi-programmed system. So first we are going to see what exactly batch systems is. So batch systems is my heading now. So what exactly the batch is? So first of all, what do you mean by batch? That we have to understand. So batch means, so the meaning of batch, it means that set of processes, batch means set of processes which has the same requirement, Set of processes which has the same requirement is called as batch systems. So as part of the batch systems, what do you mean by batch? Set of processes which has the same requirement. Let's say if you consider one example, I have process P1, process P2, process P3 and process P4. Process P1 execution time, the process P1 execution time is, let's say, 5 minutes. The entire 5 minutes of execution is with only CPU. If you consider process P2, it is having execution time of 10 minutes, but this execution time is composite of CPU and IO. 5 minutes with the CPU and 5 minutes with the IO. Then you have P3 which has 5 units of execution. So that execution time entirely it is with the CPU only. Then you have process P4 which has again execution time of 10 minutes. Among that 5 minutes is with the CPU and 5 minutes with the IO. Then now among these 4 processes, if you understand the batch definition, how many batches you can create? You can create 2 batches. What are the 2 batches? The first batch is P1 and P3 because they have the requirement of only CPU. So P1 and P3, these are one batch. I can say this is batch 1. P2 and P4, these two are one batch because they have, along with the CPU, IO requirement is also there. So P1, P2 and P4 belongs to, let's say, batch 2, right? So now this batch systems is a uniprocessor system. It is a uniprocessor system. So what does it mean? It is having only one processor in it. Only one processor. So it means that if you consider a diagram like this is your uniprocessor system. So in this system, you have the CPU here, only one CPU, and you have IO here. And this is your main memory. So this is your memory. So now, how many number of processes can be loaded into the main memory with respect to these batch systems? That is what our next concept. So first point is we have defined what do you mean by batch. After defining what do you mean by batch, then we are going to see the second point is how the processes can be loaded into main memory. So that is what our second point. So here multiple programs can be loaded into main memory. Nothing wrong in that. Multiple programs can be loaded into main memory. Multiple programs can be loaded into main memory. Okay, multiple programs can be loaded into main memory at a time, but batch wise. So strictly it is but batch wise. So but batch wise multiple programs can be loaded into main memory. So here we have 2 batches. Among the 4 processes we have made 2 batches. So batch wise they can load into the main memory. Let's say first I am loading P2 and P4 here. So now the memory is having these 2 processes, P2 and P4. So what is the execution time of this P2? 10 minutes. And what is the execution time of this P4? 10 minutes. And among the 10 minutes, 5 minutes with the CPU and 5 minutes with the IO, 5 minutes with the CPU and 5 minutes with the IO. So for example, first we have handed over this process P2 to the CPU. Let's say at 0, we have given this P2 to the CPU. So it means that this P2 is going to get executed on the CPU from 0 to 5 minutes of time. From 0 to 5 minutes of time it is going to be executed. Then this P2, as its CPU time is over, then it is moving to IO operation, because we mentioned that 5 minutes with the CPU and 5 minutes with the IO. So now it is moving from CPU to IO. So means P2 is moving now. So this is going to be executed here, let's say 5 to 10. So P2 is executing on the IO between 5 to 10. But by that moment, while this P2 is in execution with the IO, then what about the CPU? The CPU is sitting idle. Then are we allowed to allot this particular P4 onto the CPU or not? While this P2 is performing its IO operation between 5 to 10, during that period, the CPU is sitting idle. Then we find that the CPU is sitting idle. Then are we allowed to allot this P4 to the CPU or not? This is what we have to know. So it is not allowed. This is not allowed. Why it is not allowed? That is the concept here. Look at, so the next point is, so second point is speaking about loading principle, how the processes can be loaded into main memory. And the third point is speaking about how the processes gets executed in this batch system. So to execute the processes in the batch system, to execute the processes, in these batch systems, we use a concept called, what is the concept called? We use a concept called, what is that concept called? Spooling. The concept name is spooling. Spooling. So what is the meaning of spool? So before going to define what do you mean by spooling, let's understand what do you mean by spool. So spool which transfer, simultaneous peripheral operations online. So SPOOL, simultaneous peripheral operations online. So in order to execute the processes in the batch systems, we use spooling concept. What is a spooling definition? That is what my fifth point. So spooling, what is the definition of spooling? The definition for the spooling is the process of placing the data in a temporary buffer, for another program to execute. This is what your spooling definition. The process of placing the data in a temporary buffer for another program to execute. So look at, I just considering this concept with the real-time example of spooling is, the real-time example for the spooling is printer. So printer is the live example which is following your spooling procedure. So if you recall printer, what is the functionality of the printer? Printing the jobs, printing the files. Let's say I have one file which contains 100 pages. I have another file which contains just 2 pages. But for example, I have given file 1 which has 100 pages to print first. I have given file 1 which is having 100 pages to print first. So while this file 1 is in printing status, then if I give printing of P2, file 2, then is the file 1 execution gets stopped and the file 2 printing can be started? No, right? So once the entire 100 pages of file 1 printing is been over, then only file 2 printing can be started. Correct, no? So it means that one entire process execution must be completed. Complete execution of a process must be completed. Completely a process must be executed. After that only the next process execution can be started. So that is called your spooling. Look at, if I correlate this, the process of placing the data in a temporary buffer. See, where I am creating this data means I can say here the file. Where I have created the file? In my laptop or else in my system. Then I am giving a print command. Let's say I have given Control P. So when I given the Control P, then this file is being loaded into printer pool. The printer pool is a temporary buffer or it's permanent buffer. It is a temporary buffer. That's what the meaning here. The process of placing the data in a temporary buffer means I have given the printout so that it is being placed into printer pool, which is a temporary buffer. So now my file is part of the printer pool. Then look at, for another program to execute. What is the another program that is going to be executed here? Printer. Printer itself, it is a program. So I have created a file and I have placed this file in a temporary buffer. Then the printer program is executing that file. This is called spooling concept. Right? So the live example in which we are still using this spooling procedure is printer. So printer is the best example for spooling concept. You can say that printer is a spooled device. So why this particular P4 is not allowed to execute, why this P4 is not allowed to load onto the CPU during the 5 to 10 minutes? Reason, P2 is not yet finished completely. P2 is just finished only 5 minutes of its execution. But what is the total execution time of the P2? 10 minutes. But the 10 minutes of execution of the P2 is not yet finished. It is in progress. From 5 to 10, P2 is on the IO. Correct? But by that moment, during the 5 to 10 minutes, while the P2 is on IO, this CPU is sitting idle. Then if you are trying to allot this P4 to the CPU, it is not allowed because P2 execution is not completely done. Getting me? So file 1 must be completely executed, means all 100 pages of the file 1 must be printed first. After that only file 2 printing can be started, even though it is having only 2 pages or else 1 page. That's what the concept here. So one entire execution of the process is being completed, then only the next process execution can be started. So in our example, P2's complete execution is 10 minutes. Until that, P4 cannot start its execution. So that is why P4 is not allowed to load onto the CPU during 5 to 10 minutes while this P2 is spending its time on the IO. So this is what your exactly batch systems is. So with respect to these batch systems, what is the drawback you are facing? The drawback of these batch systems is, CPU idleness. CPU idleness is the drawback of these batch systems. Because 0 to 5 to 10 minutes, while during this 5 to 10 minutes P2 is on IO, during the time the CPU is sitting idle. You are not allowing this P4 to schedule onto the CPU. It means that the CPU is sitting idle at that moment. So if you are increasing the idleness on the CPU, then what will happen? What will happen? The system throughput is going to get low. So that's why the drawback of these batch systems is CPU idleness. So what is the real-time example for this batch systems is, the real-time example for this batch systems is IBM operating system. IBM operating system version 2 is the real-time example for these batch systems. So this is what the explanation about batch systems. So what is example? What is the example device for the spooling concept? Printer. Just look into this. Look into these two words and look at the question which we have. Look at this question. Which of the following is an example of spool device? So directly, without any hesitation, you can verify for, in the options, you can verify for a device called printer. So if you verify them, then you can find a line printer is there. A line printer used to print the output of the number of jobs, which is the correct answer for this question, because the printer is only the device which is still following the spooling concept. So if you have clarity about the concepts, then you can easily handle these 3 questions. These type of questions we have from introduction and background of operating system, which is the first main topic of operating system syllabus, right? So this is one type of operating system, which is batch system. Now we are moving to another type of operating system, which is multi-programmed system. So now we are going to see multi-programmed system. Multi-programmed system. So coming to the multi-programmed system, this is also a uniprogrammed system. This is also a uniprogrammed system. So it means that if you consider this is a system, if you consider this is a uniprogrammed system in which you have one CPU, you have IO, and here you have the main memory. So what could be the first point in the multi-programmed systems is loading. So how you can load the processes in this into main memory of this multi-programmed system? That is multiple programs. That's what the first point. Multiple programs can be loaded into main memory. Multiple programs can be loaded into main memory at a time, but not batch wise. But not batch wise. But not batch wise. So it means that according to our previous example, whatever the example we have considered here, we are having 4 processes here, right? So all these 4 processes we can load at the same time into the main memory. It is not required batch 1 must be loaded first and then batch 2, or else batch 2 must be loaded first and then batch 1. Such type of condition were not there. So we can load multiple programs at the same time, but not batch wise. So it means that I can load, let's say, first I can load P2, then I can load P1, then I can load P4, and then I can load P3. So multiple programs can be loaded into main memory at a time, but not batch wise. So now, how the jobs gets executed? So for example, as you know that the P2 execution time is 10 minutes. Out of 10 minutes, first 5 minutes is with the CPU, and the next 5 minutes is I/O. So it means first at 0 to 5, from 0 to 5, P2 is on the CPU. So once its CPU time is over, then this P2 is moving on to the I/O to execute this I/O operation from 5 to 10, let's suppose. So while this P2 is in execution on the I/O, by that moment we observe that the CPU is idle because P2 is moved from CPU to I/O to perform some I/O operation. So while it is performing its I/O operation between 5 to 10, then what about the CPU? It is sitting idle. Then what you have to do? Are we allowed this P1 to allot onto the CPU or not? Are we allowed this P1 to allot onto the CPU or not? Yes, we are allowed this P1 to load onto the CPU. But in the case of batch system, it is not allowed. But this here, it is allowed to execute on the CPU. While the P2 is performing its I/O operation, this P1 is allowed onto the CPU. So it means that the main goal of this particular multi-programmed systems, CPU should always busy. CPU should be always busy. CPU should be always busy with some process. The CPU should be always busy with some process. This is what the main goal of your multi-programmed system. So that is why, while this P2 is in execution on the I/O from 5 to 10, you are allowed to execute this P1 onto the CPU because CPU should not be idle. That is the main goal of this multi-programmed system. So in order to meet that, we are allowing this P1 to execute on the CPU while this P2 is performing its I/O operation. So since we are not allowing the CPU, since we are not allowing the idleness on the CPU, what is the advantage we can have comparatively batch systems? So the advantage with these multi-programmed systems is, you can say that it is generating more throughput. So more throughput it can generate, more throughput can be generated than batch systems. More throughput can be generated by these multi-programmed systems than batch systems. This is what the advantage with this. So, and coming to the next one, coming to the fourth one, so this particular multi-programmed systems can have a drawback. So what is the drawback of this multi-programmed systems is, it is not much user responsive. Not much user responsive than multitasking systems, MTS, multitasking systems. Right? So like this you can have some important points with respect to multi-programmed systems. So the real-time example for the multi-programmed systems is, currently whatever the operating systems we are having like Windows, Unix, so these operating systems comes under these multi-programmed systems only. So please look into the first 2 points. If you look into these first 2 points, you can easily able to answer one previous year gate question here. But that previous year gate question, I just modified it, and accordingly you have to say the answer. I just converted that previous year gate question into MSQ. As we are having MSQ type of questions in our examination, just have a practice on answering these MSQ questions. So look at the question based on this multi-programmed systems. This is the question we have. Which combination of the following features must suffice? I am telling you must suffice. I just changed this word. Actually the previous year gate question is having will suffice, but here I made it to must suffice to characterize an operating system as a multi-programmed operating system. So option A, if you verify, more than one program may be loaded into main memory at the same time for execution. Option B, if a program waits for certain events such as IO, another program is immediately scheduled for execution. Option C, if the execution of a program terminates, another program is immediately scheduled for the execution. And option C, all of the above. So what is the answer for this question? If you consider, this is the MSQ question. I told you already, this is the MSQ question. So what can be the answer for this question? You can say both option A and option B are the answers for this question. Why not option C? Option C, it is the feature of uniprogrammed system also. In the uniprogrammed system also, once one program is being completed, then immediately the next program can be loaded into main memory for the execution. Right? So here, this can be happened in both uniprogrammed system as well as multi-programmed system. So that's why option C is not an answer here, as it is the combination of, as it is the common feature of uniprogrammed system and multi-programmed system. But if you look into these first two questions, or first two options, comparatively your uniprogrammed systems, what is the meaning of uniprogrammed system? You are loading only one program in the main memory at all time. But in the multi-programmed systems, you are loading multiple programs at the same time into the main memory. So it is a must and should characteristic. Comparatively uniprogrammed systems, it is must and should. And look at the next one. If a program waits for certain events such as IO, that's what we have explained in our thing, like your second point to explain that I clearly mentioned. While this P2 is performing its IO operation during the 5 to 10, then immediately you are allowing this P1 onto the CPU. Yes, that's what the statement it is given. So if a program waits for certain events such as IO, another program is immediately scheduled for execution. Yes, it is possible in the multi-programmed systems only, comparatively your uniprogrammed system. Right? So comparatively your uniprogrammed systems, these two are the must and should characteristics in order to say that the particular operating system is multi-programmed operating system. So hence I can say A and B are the correct answers for this question. This option C is not answer for this question, because this particular question, this particular statement, or this particular option C is combination of both uniprogrammed system and multi-programmed system. See, I clearly mentioned that must is been there. Right? So this is what the explanation. See, if you want to answer these type of MSQ questions, you must be well aware of the theory, the concept of multi-programmed systems. Not only this multi-programmed system, any question which is MSQ type of question, you must be well known about the theory concepts. Right? So these are the expected topics. I mean, these are the important topics from introduction to your operating system. I mean, introduction or background of operating system. So we have covered first location, which is dual mode of operation, and then we have covered various types of operating systems. Among that, we have covered batch systems and multi-programmed systems. So now we are moving to the next main important topic of operating system syllabus is process management. So this process management, as I clearly stated, that we are having three types of, we are having huge amount of theory in the under this process management. That theory we have divided into three parts. So we are going to see part-wise, already we have pointed out in our previous session part-wise important topics. So the same I am following here. if you consider process management part 1, the important concept, if you verify in our previous session, you can find that I have given the priority to this process state diagram. There I clearly mentioned that process state diagrams we are having 3. One is 2-state diagram, another one is 5-state diagram, and another one is 7-state diagram. So like this we are having a process state diagram can be discussed in 3 cases like 2-state, 5-state and 7-state diagrams. Among that, the most important one is this 5-state diagram, as we have previous year get questions from this 5-state diagram. So let's recall the 5-state diagram and then we can go the previous year get questions which we have, right? So, but I have modified them. Some might be converted to MSQs. So if you are having the concept of this 5-state diagram, then you can easily able to answer those questions. Just remember the diagram of this 5-state diagram. Look at, so for example, if you consider 5-state diagram here, if you consider the 5-state diagram here, 5-state diagram, so basically in the 2-state diagram of a process, we have only 2 states. What are the 2 states we are having? One is not running state, and another one is running state. One is not running state and another one is running state. So what is not running state and what is this? So initially in the 2-state diagram we are having only 2 states like not running state and running state. What is the meaning of not running state? Initially all processes are in not running state, means they might be in creation. They are in construction. That is called not running state meaning. What is the meaning of running state? The processes are ready for execution and they are loaded into main memory, means they are loaded onto the running state. Onto the CPU you have selected one process, that is called running state. So in the not running state, the processes are completely created. They are completely created and ready for execution. So among those ready for execution processes, only one process gets selected and that process can be loaded onto running state. This is what the meaning of not running state and running state as part of your 2-state diagram. Then if you look into this 5-state diagram, so the not running state, the first point I can write like this: not running state of 2-state diagram of a process, is divided into 2 further states. What are the 2 further states we are having? That is, first one you can call it as ready state, and another one is waiting state. Ready state and another one is waiting state. Right? And this is what my first point. Then coming to the second point, I can write like this: for good measure, we added the following 2 additional states to a process. The following 2 additional states to a process. So what are the 2 additional states we have added to the process? They are, first one is new state and another one is exit state. So here you can see new state, exit state, ready state and waiting state, means here totally you can find 4 states. Then what is the 5th state? Your running state. So overall all these 5 states All these five states of a process can be visualized like this. The diagram for, by inclusion of all these 5 states, you can draw the diagram of process 5-state diagram like this. So what is a process 5-state diagram here? If we verify, let's say this is your new state, and this is your ready state, and this is your running state, and this is your exit state. And here you can have your waiting state. So from here to here, a process can move. This transition is called as admitted. From ready state, among the multiple ready queue processes, one process must be selected onto the running state. This transition is called scheduled, or else you can say that dispatched. And while a process is in running state, a process can move from running state to the ready state. A process can move from running state to the ready state. So when a process can move from running state to the ready state, in the sense when there is a timeout or else interrupt is occurred, when there is a timeout or interrupt is occurred, by that moment a process while it is running, it can move from running state to the ready state. Then and one more, while a process is in running state, if there is any IO event is occurred, then that particular process can move from running state to the waiting state. After finishing of this IO operation, this is what your IO event is finished. So after finishing of your IO operation, then you are entering into ready state. So like this, a process is keep on moving between these states. So at any particular time, if a process is part of these 3 states, that means that particular process is part of your main memory. So this is what your logically this is called your main memory, right? So once a process is completely finished, it means that its IO operation is over as well as its CPU operation is over. Then that particular process can make a transition from running to exit. So this is what your 5-state diagram of a process. So if you verify this, if you remember this diagram, you can easily able to answer some questions based on this process state diagram. Look at the questions here. This is one question we have. Consider the following process state transitions for a system using preemptive scheduling. Which of the following are true? Option A, it is mentioned that a running process can move to the ready state. Verify. According to the given diagram, a running process can move from the ready state. Is it true or not? Yes. When it happens, when there is an interrupt or else timeout is occurred. So it means this transition is possible. This is a valid transition. This is possible. Look at option B. A ready process can move to the running state. A ready process can move to the running state. Have a look. If you verify, a ready process can move onto the running state, which is true. Which is true, right? So it means that this particular transition is also a valid transition, means true transition. And look at option C. A blocked process can move to the running state. A blocked process in the sense waiting process. A process which is part of the waiting state can move to the running state. Is it valid transition? Have a look in the diagram. Waiting to running, or we have any transition? No, we have a transition from running to waiting. We don't have a transition from waiting to running. So it means that this particular transition is invalid. Then a blocked process can move to the ready state. A blocked process in the sense that is moving from, that particular process is moving from waiting to ready. So look at waiting to ready. It is moving from waiting to ready. So this is valid transition, right? So this is valid transition. So overall, if you verify, as it is clearly mentioned that true. So among all these options, option A is true, option B is true, and option D is also true. So this is also a kind of MSQ question. So this kind of questions you are able to answer once you are clear about the concepts. Right. So let's look into one more question. Look at this is the question we have. In the following process state transition diagram for a uniprocessor system, assume that there are always some processes in the ready state. Now consider the following statements. This question. So this is also a MSQ kind of question. Please observe that this is also a MSQ kind of question. So please look into this question statements, I mean options and this diagram. Please verify this diagram and look at these particular options. Option A, what it is saying, if a process make a transition D, if a process makes a transition D, what is the transition D? Verify. Transition D means a process is moving, transition D means a process is moving from running to termination. Then look at the statement. If a process makes a transition D, it would result in another process making transition B immediately, transition B immediately. What is the transition B? Immediately one process is moving from ready state to the running state. Yes, it is true. This is resulting, this transition is resulting this transition, which is true because you are using multi-programmed systems. In the multi-programmed systems, the CPU should be always busy. And it is clearly mentioned that there are always some processes in the ready state, means it is multi-programmed systems it is speaking about. So the main goal of multi-programmed system is making the CPU always busy, means one process must be always present in the running state. So when a process is making a transition D, means a process is leaving the CPU, then immediately one process from the ready state must be selected onto the running state, which is true statement. So option A is true statement here. This is true. Then look at option B. If a process P2 in blocked state can make a transition E, while another process P1 is in running state. Look at, while one process is in running state, let's say P1 is in running state here, then P2 can move from blocked state to ready state. This transition is possible or not while this P1 is in running state? Yes, these two are independent activities, no? So it means that this is also a true statement. So while P1 is in running state, P2 can make a transition, or else P2 can move from waiting state to ready state, which is possible. So this is also a true transition. Then option C, if you verify, the OS uses preemptive scheduling. Is it true? Yes, it is also a true statement. How you can say that this is a true statement? Because preemptive and non-preemptive, you must be aware of the definitions of preemptive and non-preemptive here. So what is the meaning of preemptive here? So the meaning of preemptive is, look at the definition for the preemptive can be written like this. Once the CPU is allocated to a process, once the CPU is allocated to a process, once the CPU is allocated to a process, the CPU is allowed to continue with the same process, the CPU is allowed to continue, the CPU is allowed to continue with the same process, until some amount of its execution time, until some amount of the process execution, until some amount of the process execution time. After that, the process is, the CPU is, after that the CPU is removed. After that CPU is removed from that process, after that the CPU is removed from that process forcibly. This is what the definition for the preemptive. So basically preemptive means preemption here. But what about the non-preemption? Once the CPU is allotted to a process, the CPU is allowed to continue with the same process until the entire execution of the process is being done, until the entire execution of the process is being completed. Then the CPU can be removed from that particular process, or else the process can release the CPU on volunteer basis. So it means that this is what the definition of preemptive and non-preemptive. But if you look at this diagram here, this transition, specifically this particular transition C, if you verify, this particular transition C, what is this transition C if you verify? Look at, according to our explanation, transition C is this one, running state to ready state, means some timeout is occurring. So means you are not allowing a process to execute until its entire execution, only some amount. It means that this transition is purely preemptive system. So once in a process state diagram, if you find this particular transition C, means running state to ready state, blindly you can say that it is preemptive system. So that's what we are saying that. So this particular statement C is true because the state transition C is being present in the given question, right? So all these option A, option C, B and option C are correct statements with respect to the given transition diagram here, right? So as we are using, as the preemptive system we are using, non-preemptive systems are not usable here. And of course, all current modern operating systems are preemptive systems only. They are not non-preemptive. They are all preemptive systems only. This kind of questions you can have from this particular process state transition diagrams, means process management part 1. Okay, so I believe you are clear with these concepts, whatever the concepts. See, we are having so many concepts in this particular operating systems syllabus that I have yesterday. I clearly defined the system, the main topics and the subtopics, and I clearly mentioned which are the important concepts among them, right? So I believe this session is helpful to you, how to handle questions. Like I emphasize mostly on MSQ questions only. So if you want to answer this questions of, if you want to answer these type of MSQ questions, you must be well aware of theory, concepts. The concepts must be well aware of you, as well as the theory also must be very clear to you, right? So this is the important concepts session based on your operating system subject. So there are so many, as we are having some time constraint, I'm able to cover these are the concepts which are important concepts, right? So I believe this session is helpful to you. Thank you.